So let's get the integral from 0 to 1 of x e to the x. Nice and simple, right? Nice and simple. This one we can do by parts, tic-tac-toe even, right? So we'll do this one, and then we'll do Simpson's rule with 4 partitions, okay? Right? Actually, let's make it easier. Let's go 0 to 4. Just because when I do the partitions, I don't want to work that much. You can see I would have had 1 over 4 for my delta x's. Now I have 4 over 4 for my delta x's when I do Simpson's rule. So the integral from 0 to 4 of x e to the x dx. So we're going to do the exact area first using tic-tac-toe, right? Let me know when anyone is there. Caleb, are you in Venice in that picture? Venice, Italy?
Yeah.
Nice. You may get there? Adam's there? Nama's there? Haoshen's there? Nice. Caleb got there? Jerusalem, right? Love it. Niant, nice. Charlene. I'll give it another minute, okay?
Do four partitions?
Yeah, we're going to do 4 partitions, exactly. So I know, Charlie, you have a hard time waiting, so go for it. So what we did here was integration by parts, right? Or tic-tac-toe. this one, if I had said to you, do integration by parts, you could have had the option of tic-tac-toe, right? And if I say to you, do it by tic-tac-toe, I want you to do it by tic-tac-toe, okay? Usually when I say integration by parts, you can't do it by tic-tac-toe. So, anybody need another minute? So, Eleanor, you got there? David, you got there? Michael? Nice. So here we go. Let's do 4 partitions. So we're going to do Simpson's rule now, right? And I want to do 4 partitions. I'm always going to, all right? The book will do more. WebAssign will do more. But it's clearly that delta x is 4 minus 0 over 4. Is everybody okay with that? So the width of each partition is going to be 1. Right? Is everybody following me here? And then my x sub i's, so x sub 0 is 0, x sub 1 is 1. I mean, I try and make it this simple every time. Sometimes I fail, but I'm trying to make it simple. What's more important here so far is that you could have done this integral by parts, right? But we want to see how good Simpson's rule is for it. And then see if the error formula we have is accurate. I didn't give that to you yet. So our area now is approximately equal to 1 over 4. Remember, it's not 1 over 4, it's 1 over 3, right? Delta x over 3. Remind me, please. Yeah, delta x over 3. So 1 over 3. And then I need coefficients of 1, 4, 2, 4, 1, right? So I need, and remember my function is x e to the x, right? I'm not doing a derivative or an antiderivative or anything like that. So I need 1 times 0 e to the 0 plus 4 times 1 e to the 1 plus 2 times 2 e to the 2 plus 4 times 3 e to the 3 plus 1 times 4 e to the 4. Is everybody with me there? Remember, I'm plugging into x e to the x with each of my x sub i's, and then I have those coefficients of 1, 4, 2, 4, 1. How are we doing? We okay? Nice, so this one's gone. It doesn't look like anything else gets real easy. I have a 4e plus a 4e squared plus a 12e cubed plus a 4e to the 4th. And that's about as good as I get. I mean, I could factor out an e, but it doesn't make that much of a difference. So I'm going to my calculator now. Anyone get there? Same thing. Nice, Serrano, thank you. Angel, thank you. Charlie, yes. Eleanor, Michael, yes. Yep. Thank you, Juan. Yeah, so if you're giving me a thumbs up, I try and acknowledge. But otherwise, the students, thank you, Charlene. Students I can see on camera, I can tell they got it or didn't get it. I can tell. Thank you, Nyan. I can tell when I say a joke and they roll their eyes. I know what they mean. Adam, gotcha. Josh. Thank you. Nice. So we got two integrals where we found the actual value, and then we did a 4 partition to get an estimate of that value of the area, and so we're going to compare both of those and look at the error, okay, and then we're going to look at the error formula we have for Simpson's rule, which is finally where we get to do a little calculus. So help me out here. I think I remember everything, but I would like you to be able to give me some numbers here. When we did the integral from 0 to pi of sine x dx, we got an actual area of 2, right? And we got an estimate of 2.004 something. What was it? 2.004. 6? Yes, 2.0046. Thank you.
Yes.
Yes, nice. And when we did the integral from 0 to 4 of x e to the x dx, we got an actual area of, help me there, what was that actual area?
164.794.
Before that, Charlie, it was e to the 4e cubed? No, 3e to the 4th plus 1? Is that right? 3e to the 4th plus 1? And then now, Charlie, now, yeah, 166 point what?
164.7945.
Thank you, Charlie. And our estimate there? 1.66, right? 166 point something.
166.616.
Thank you. 6161, yeah. Nice. So let's just calculate an error real quick, which is very simple, right? It's just the absolute value of the actual minus the estimate, right? So absolute value of 2 minus 2.0046. That one I don't need much help with. 0.0046. Right? That's our error. And then our other error here, our error in the second method was 166.6161 minus 164.7945. We don't care about if it's an error above or below. We just care what's the error. Okay. So 1.8216. We agree? 1.8216. Anybody give me a yes or something? Yes, thank you. Thank you. Nice. So let's look at our error estimate and then be ready to go. What? Our error estimate for Simpson's rule, which we're going to put on our formula sheet. This is in 5.9. And again, I'm not giving homework in 5.9. Web assigns enough, okay? Our error for Simpson's rule is E sub s in absolute value, so positive only, right? K is less than or equal to k times b minus a to the 5th over 180 times n to the 4th. Okay. And so so b minus a should be obvious, right? It's the integral from a to b, right? So b minus a is obvious. N is the number of partitions. So a and b are the bounds of the integral. N is the number of partitions. K is the max of f quadruple prime of x on AB. And we want to make it, we want to go to the next integer. So we want to go K as the closest integer above the max, right? So if I get 1, I can use 1. But if I get 0.9, I want to use 1. Does that make sense? If I get 1, I can use 1. If I get 2, I can, sorry, if I get 1.2, I want to use 2, right? So I want to get to the next integer above the max of the fourth derivative. Is it crazy or what? On that closed interval, right? And then that should give me an upper bound for the error. So meaning in the first problem, I should get something bigger out of that formula. I should get something bigger than half a penny, right? Something bigger than 0.0046. So like 0047 or 005, right? Does that make sense? I should get an upper bound on the error. All right, well, the first one's easy. The second one's not easy. The first one's easy, right? We want to get, we know b minus a is pi minus 0, correct? So for the integral from a to b of sine of x dx, sorry, 0 to pi, right? Well, think about the fourth derivative there. What's the derivative of sine? Cosine. What's the derivative of cosine? Negative sine. What's the derivative of negative sine? Negative cosine. What's the max that cosine will hit? Plus or minus, it doesn't matter, it's 1. So for this one, k is 1, right? So sine and cosine, right, they keep oscillating back and forth. The max that sine or cosine will ever hit is 1. And again, we want that kind of be an absolute value. We're not going to use a negative there because, right, even though the derivative is really negative cosine, the fourth derivative is negative cosine, we're not going to use the negative because we're looking at a positive error. So k is 1. B minus a is pi minus 0 is pi, right? N is 4. So let's look at what our error is. It's 1 times pi to the 5th over 180 times 4 to the 4th, right? N is 4 partitions, right? And so what do I get for this? Pi raised to the 5th divided by 180 divided by 4 to the 4th. So is that bigger than the error I got? Right? Is that greater than or equal to 0.0046? Is 66 cents bigger than 46 cents? Yes. So my error estimate works. Oh my God, don't ask me where this error estimate comes from. I don't even know. I guess I could look it up. I'm sure I talked about it in grad school, but I just love the fact that there's a fourth derivative in here. I think it's fascinating, right? If we think about, and you'll see there's nth derivatives in other places too, right? Remember, we used to go up to first derivative test, second derivative test. Now we got a fourth derivative that's in play. So it's definitely a little bit interesting. Let's do this last one. And of course, the last one, the issue is the k value. So if my function is x e to the x, I need 4 derivatives of this. And then I need to find the max. So we want to find f quadruple prime of x on 0 to 4, and then see what we get. Hopefully it's not horrible. So I'll race you. Ready? Oh, it's not bad. Figure it out. Melky, did I forget a 5 somewhere? Are you saying I forgot a 5 on my last work? Melky, you there? Oh, where did it come from? I gotta get back to you. I gotta get back to you on that. I don't know yet. It's pretty sad. So when I look at this function, I see it's increasing. It should be obvious that it's increasing. So I know I'm going to get my max at 4, right? When I look at this fourth derivative, I see at 4 is where I'm going to get my maximum value. So f quadruple prime at 4 is 8 times e to the 4. So it's 436.7, 7852. So I'm going to use 437 as my k. Next integer up above. So I'm getting 437 times 4 minus 0 to the 5th over 180 times 4 to the 4th, right? Partition to the 4th. So 437 times 4 over 180. My pad just closed. I'm having a technology issue here. Here we go. My computer's bored with the lesson as well. I'm running out of